curious minds, welcome back to ProjexCellence ProDigy, your one-stop destination for engaging and simplified project management concepts. In our Evergreen Mechanical Series, today we are taking up a very crucial topic, thermodynamics. In this video, we will understand what thermodynamics is, and we will explore all 4 laws of thermodynamics using clear explanations and real-life examples. You know me well by now. I am Govind, a PMP certified professional and a mechanical engineering graduate with over 25 years of work experience in power plants and the utilities sector. So let's get started and make thermodynamics simple, practical, and easy to understand. What is thermodynamics? Thermodynamics is the branch of physics that deals with energy, heat, work, and temperature. It helps us understand how energy is transferred and how it changes from one form to another. Now let me simplify this. Whenever something heats up, cools down, moves, or does work, thermodynamics is involved. Let us take a simple kitchen example. When you boil water using an electric kettle, so what happens? The electrical energy is converted into heat energy, and that heat flows into the water, which raises its temperature. Thermodynamics explains how energy flows, where the energy came from, and where it finally went. It explains how engines produce power, and also why engines become hot. Think about a car engine or a diesel generator. What happens? Fuel burns inside the engine and heat is produced. That heat pushes the piston downward, and the piston, which is connected with connecting rod and crankshaft, produces useful mechanical power. Next, let's talk about air conditioners. What air conditioner does? It removes the heat from your room and throws it outside. But it cannot do this on its own. That is why air conditioners need electricity. Here, the thermodynamics tells us that heat cannot flow from a cold place from inside to a hot place outside without external work. So you need some external work. So that is provided by electricity. Now comes a very important point. No machine in the world is 100% efficient. In every engine, some energy is lost through exhaust gases, some through cooling water, and some due to friction. So thermodynamics explains why some energy is always wasted. Even your mobile phone proves this. When you use it, the phone becomes warm. That heat is energy loss. Thermodynamics is used everywhere. In power plants, IC engines, in refrigeration and air conditioning, in chemical reactions, and even in renewable energy systems like solar power plants. So whenever energy is produced, transferred, converted, or lost, thermodynamics is working silently in the background. To understand this subject properly, we must first understand its 4 fundamental laws. Each law gives us one important principle about temperature, heat, energy conservation, and entropy. These laws are extremely important in mechanical engineering because they help us understand how engines, turbines, compressors, boilers, refrigerators, and many other systems actually work. So let's begin with first foundation, the Zeroth law of thermodynamics. This states if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. Let me explain this step by step. Imagine 3 objects A, B, and C. If object A is in thermal equilibrium with C, means the temperature of A is equal to temperature of C and object B is also in thermal equilibrium with C, means the temperature of B is equal to temperature of C. So automatically A and B must have the same temperature. This simple idea is the foundation of temperature measurement. Let's understand this with a daily life example. When you place a thermometer under your tongue, heat flows from your body to the thermometer. And this heat transfer continues until no more heat flows between your body and thermometer. At that point, both your body and the thermometer reach the same temperature. This condition is called thermal equilibrium. And that is exactly why the thermometer is able to show your body temperature accurately. So the zeroth law tells us that temperature equality is the basis of all thermal measurements. You might be thinking, why do we call it the zeroth law? The interesting part is that it was actually discovered after the first and second laws of thermodynamics. But scientists later realized that this concept is more basic and fundamental than first law and second law. Since temperature measurement itself depends on this law, so it was placed before the first law and second law and named the zeroth law. First law of thermodynamics. It says energy can neither be created nor destroyed. It can only be converted from one form to another. That is why this law is called the law of conservation of energy. Let me explain this in simple terms. Whatever energy goes into a system must either come out of the system or remain stored inside it. This idea can be written mathematically as energy in minus energy out equals change in energy. Or in thermodynamics form, Q equals W plus delta E. Here, Q is the heat supplied to the system and W is the work done by the system, and delta E is the change in internal energy. Now let's connect this to a real life engine example. In an internal combustion engine, fuel is supplied to the engine as chemical energy. And this fuel energy does not disappear. A part of it becomes brake power, which is the useful output at the crankshaft. And some energy is lost as friction in bearings and moving parts. Some energy is carried away by hot exhaust gases, and some energy is removed by cooling water to prevent the engine from overheating. And the remaining energy is lost as radiation to the surroundings. So when you add everything together, total fuel energy input equals brake power plus friction losses plus exhaust losses plus cooling losses plus radiation losses. This clearly proves that energy is conserved, not destroyed. And that is exactly what the first law of thermodynamics tells us. Second law of thermodynamics. It tells us something very important about how energy actually behaves in the real world. We just saw the first law says energy cannot be created or destroyed. It only changes form. The second law goes one step further. It tells us how energy naturally moves and why energy system can never be perfectly efficient. In simple terms, the second law explains two key ideas. One is heat always flows naturally from hot objects to cold objects. And second, whenever energy is converted, some of it becomes unusable waste heat. Imagine you make a cup of hot tea and leave it on the table. After some time, what will happen that the tea becomes cooler. Why does this happen? Because heat moves from a hotter object to a cooler surrounding. The hot tea slowly loses heat to the surrounding air. And in reality, the air in the room becomes very slightly warmer. But the room is so large compared to the small amount of heat in the cup, so we cannot notice this temperature change. But here, the important point is the direction of heat flow. Heat moves from hot tea to the cooler surroundings. The two statements are very popular while understanding the second law of thermodynamics, the Clausius statement and Kelvin-Planck statement. Clausius statement. It says, heat cannot move from a cold object to a hot object by itself. It needs external energy to do so. Let's understand this with a refrigerator. Inside your refrigerator, the temperature of food is usually around 4 degrees Celsius, while the room temperature outside may be about 25 to 30 degrees Celsius, depending upon the season or weather. Now, according to natural heat flow, heat should always move from hot to cold. That means heat should actually flow from the warm room into the colder refrigerator. If that happens, the food inside the fridge would slowly become warm. But we know that refrigerators keep food cold. So how does this happen? Many people think that the refrigerators send cold air inside, or in case of air conditioner, it supplies cool air into the room. But thermodynamically, that is not the real story. In reality, refrigerators and air conditioners do not create cold. What they actually do is remove heat from a colder space and throw that heat outside into a warmer space. This means heat is being forced to move from cold to hot, which is opposite to the natural direction of heat flow. To do this, we need external work. And in refrigerators and air conditioners, this work is provided by electricity. Electric power runs the compressor, and the compressor circulates the refrigerant to carry heat out of the refrigerator and reject it into the room. So instead of sending cold air inside, the system is actually pumping heat outside. This is a perfect real-life example of the second law of thermodynamics, which tells us that to move heat from cold to hot, external work is always required. Now let's look at the second statement called the Kelvin-Planck statement. It says that no heat engine can convert all the heat supplied to it into work in a cyclic process. Let's take a car engine as an example. Suppose it produces 100 units of heat energy. What happens? About 25 to 30 units become useful work, which moves the car, and the rest is lost as hot exhaust gases, heat removed by radiator cooling water, friction in engine parts, and heat radiated from the engine. So out of 100 units, only about 30 units do useful work. The rest becomes waste heat. This is why no engine can ever be 100% efficient. This clearly illustrates the second law of thermodynamics. So in simple words, heat naturally flows from hot to cold, not the other way around. And no engine can ever be 100% efficient. And some energy is always wasted as heat. That is the essence of the second law of thermodynamics. Now let's understand the third law of thermodynamics. It states that at absolute zero temperature, the entropy of a perfectly ordered crystal becomes zero. Before understanding this law, we need to know what entropy actually means. Entropy is simply a measure of disorder or randomness in a system. In simple words, entropy tells us how organized or disorganized a system is. Let's take a simple example. Imagine your study table. If all your books are neatly arranged and everything is properly organized, the system is orderly. In thermodynamics, we would say the system has low entropy. Now imagine the same table with books scattered everywhere and paper mixed up randomly. That situation represents high entropy because the system is more disordered. So the basic rule is simple. More disorder means higher entropy. Now let's understand entropy using temperature. In a cold object, molecules move slowly and remain relatively organized. Because of this, cold objects have lower entropy. But in a hot object, molecules move faster and more randomly. This increases disorder. So hot objects have higher entropy. So as temperature increases, molecular motion increases and entropy increases. Another very common example is ice melting. In an ice cube, water molecules are arranged in a fixed and orderly structure. So ice has low entropy. But when the ice melts and becomes water, the molecules are free to move around randomly. So this increases disorder. So liquid water has higher entropy than ice. Now let's connect this idea to the third law of thermodynamics. A perfect crystal is a substance where all atoms are arranged in a perfectly ordered pattern. At absolute zero temperature, which is 0 Kelvin or minus 273.15 degrees Celsius. At this point, molecular motion theoretically stops completely. The atoms stop vibrating and remain fixed in position. So there is no randomness in the system. And when there is no disorder, the entropy becomes zero. And this is the lowest possible entropy a system can have. In real materials, crystals are not perfectly ideal. They often contain some defects. So because of these imperfections, real materials may still have a very small amount of entropy, even at very low temperature. But the key idea remains the same. What is that? At 0 degree Kelvin or minus 273.15 degrees centigrade, entropy is minimum. And as temperature increases above 0 degree Kelvin, molecular motion increases, randomness increases, and therefore entropy increases. If we talk about practical applications of the third law of thermodynamics, it is used to determine absolute entropy. Since we know the entropy of a perfect crystal at 0 Kelvin is 0, scientists use this as a reference point to calculate entropy values of substances at different temperatures. And these entropy values are very important in thermodynamic tables and chemical reaction calculations. The second application is in cryogenic engineering, which deals with extremely low temperatures. This is used in producing liquid nitrogen, liquid oxygen, and liquefied natural gas, which are widely used in industry and medicine. Another interesting application of this law is superconductivity. At extremely low temperatures, some materials behave in a very unusual way. They lost their electrical resistance completely. Normally, when electricity flows through a wire, some energy is always lost as heat because electrons collide with atoms inside the material. This is what we call electrical resistance. But in certain materials, when the temperature becomes very low, the atoms hardly vibrate at all. Because of this, electrons can move through the material without any obstruction. As a result, electrical resistance becomes zero. And this phenomena is called superconductivity. Now, this principle is used in some very advanced technologies. For example, MRI machines in hospitals use superconducting magnets to create extremely strong magnetic fields. These magnets require very high currents, and superconductors allow current to flow without energy loss, which makes MRI machines efficient and stable. Another exciting example is magnetic levitation trains, also known as maglev trains. These trains use powerful superconducting magnets to create magnetic forces that lift the train above the track. Since the train does not touch the rails, there is almost no friction, and which allow the train to travel at very high speeds. Third law also tells us something important about cooling limits. It states that absolute zero temperature can never be reached in practice. So this helps engineers understand the ultimate limits of refrigeration and cooling systems. So the third law is not just theoretical. It plays an important role in low temperature technology, chemical thermodynamics, and advanced engineering systems. Thermodynamics is not just theory. It is the science that controls how energy powers our world. Thank you for watching. If you found this lesson helpful, please like, share and subscribe to ProjexCellence ProDigy. Until the next lesson, keep learning and keep exploring. Namaste, goodbye, Sampai Jumpa.